So good afternoon, everyone, and welcome to another edition of the CIRI webinar series. My name is Elena Buss, and I'm a Senior Research Program Manager for the Critical Infrastructure Resilience Institute here at the University of Illinois. I am delighted to have the pleasure this afternoon to introduce you all to our presenter, Dr. Dilkina. Dr. Dilkina is an associate professor of computer science at the University of Southern California and the co-director of the USC Center for AI and Society. She is an AI expert with a focus on discrete optimization, network design, and the integration of machine learning and combinatorial optimization. Dr. Dilkina is one of the facility leaders in the young field of computational sustainability, fostering research on use-inspired computational methods to help solve some of the key challenges concerning environmental, economic, and societal issues on the path forward to a sustainable future. She has made key contributions on using artificial intelligence for biodiversity conservation, disaster resilience, infrastructure mitigation planning, and climate impacts. Today, she will address her work titled Leveraging AI for Disaster Resilient Infrastructure Mitigation Planning. This research is funded through CIRI by DHS and the Office of University Programs. I want to thank Dr. Dilkina and everyone on the line for joining us today. I'd like to remind you all to please keep your mic muted while the presentation is taking place to be considerate of all of our participants. However, I invite you to unmute yourself to ask questions, and we'll also be monitoring the chat. So if you're more comfortable asking your question there, we'll make sure we get it answered. So without further ado, I will turn it over to Dr. Dilkina, and thank you all for being here.
Thank you, Lena. Thank you for the nice introduction, and thank you everybody for having me. And I'm so excited to share some of my work that I have done on using AI algorithms for disaster resilience. So let me start sharing. Okay. Okay, so everybody can see my screen, right?
Looks good.
Excellent, thank you. So as you all know, natural disasters are increasing in frequency and severity across the world and the US, and that makes a lot of our critical infrastructure systems even more exposed to damage. In particular, flooding submerges roads and accelerates road degradation, and is one of the natural disasters that we have seen increase also in severity and frequency. In particular, it stands out across other natural disasters as one of the most impactful. In fact, 52% of deaths and 44% of economic damages from natural disasters across the world are attributed to floods, according to statistics from 2017. So flood impacts on road infrastructure has impacts mobility in terms of longer emergency response time, increased evacuation time, and reduced transportation of goods and raw materials. It has economic impacts in terms of cost of repairs and loss in productivity. So mitigation planning here can help us reduce some of these impacts by investing ahead of the disaster into our critical road infrastructure. Similarly, earthquakes are another natural disaster that that has great impacts. In particular, it's very relevant to where I live in Los Angeles, where we are a very high seismic zone. In particular, for example, an estimated possible earthquake of a magnitude of 7.8 on the San Andreas Fault in California could cause about 24 billion in business interruptions losses due to water supply interruption alone. So earthquakes can damage underground water pipe networks, and they do. And in doing so, they cause service disruptions like reduced effectiveness of disaster response. For example, the fire department, hospitals, and disaster recovery centers cannot fully operate without water, and loss of public access to water, which can cause big health impacts. And obviously, similarly, again, economic impacts in terms of cost of repairs loss in productivity. So similarly to the flood hazard risk, earthquake hazard risk have big impacts on our critical infrastructure, in particular water pipes. So in the talk today, I want to show how we have designed data-driven mitigation planning algorithms to address those two challenges. So we want to design ways in order to do targeted infrastructure network fortification to maximize resilience. We need to choose components of these networks and upgrade them ahead of time so that to minimize the impact of the hazards. So what does this translate to specifically? So in the flood setting, we are going to look at the following problem. Given a road network and flood risks, we need to decide how to upgrade roads in order to minimize resilience to floods and other disasters. In particular, we're going to look at resilience in terms of mobility, the ability of people to move from one part of the urban area to another. Why is this problem difficult? It's because we need to implement mitigation planning under limited budget, so we cannot just upgrade everything that is at hazard risk. And
let's go, rock and roll.
Out of all the flooded, exposed to flood risk segments, we need to select some subset. And so selecting this subset under a restricted budget is actually has exponential number of possible solutions, and so it's really hard for humans to decide upfront without the help of an algorithm. And other challenges arise from the fact that we might want to balance different metrics like cost and benefits, and also our ability to actually recognize and have data on the mobility needs across different urban centers. Similarly, in a very kind of parallel spirit, we want to be able to do mitigation planning for our water pipe network. So here we are given a water pipe network and earthquake risks, and again we want to select parts of the network, edges of this network, to replace. So we want to replace some water pipes with seismically resilient pipes, which essentially will hopefully guarantee that under these earthquake scenarios, they will still continue to function. And we want to do that again strategically across a bigger area in order to optimize for desired results. In our case, the desired results that we are aiming for is that we want to guarantee that critical customers like hospitals, fire, police stations, evacuation center, etc., are directly connected to this resilient subnetwork of pipes that are either not exposed to earthquake hazards or have been upgraded through the mitigation plan. In addition to guaranteeing connectivity to water for critical customer, one more constraint that we would want to address is the fact that we want all parcels across the area to be within 1 mile of this resilient water pipe network. And this requirement essentially guarantees that it will be reachable by a fire hose, which is about 1 mile long. So similarly to the first problem, we have a limited budget to implement our mitigation plan. We have this large network of components, our water pipes. We need to select a subset to a subnetwork, and we have these complex constraints about connectivity to specific critical customers and coverage of every single household by a 1 mile radius. So both of these problems are very challenging and involve these complex constrained network design problems. So we have developed this data-driven framework for flood resilient road mitigation planning, which takes as input data on the road network, which is available actually through something like OpenStreetMaps. Combined with flood risk scenarios, we can use, for example, the ones estimated by FEMA, which are basically spatially explicit maps of where particular flooding might occur. And then we combine those to discover what are the parts of the road network that are exposed to flood risk. So in this particular area, which is Washington, D.C., we see that about 7.2% of the roads are at flood risk under this 500-year flood risk scenario. And then so that alone, it kind of gives us the the infrastructure exposure. But what is the human exposure because of those roads being potentially disabled for mobility? Is we can combine this with data on mobility needs, which basically tells us how many daily trips need to be made from one census tract to another census tract within this city. And so combining historic mobility data with these flood exposure roads, we can estimate how many of those trips will be infeasible if all of those roads were to be flooded and disabled for passage. So although only, for example, in this area, 7% of the roads are exposed, actually 32% of the mobility needs are exposed to risk, so a much bigger impact. So with these estimates, now we want to use those to guide our mitigation planning. So what we want to do is we want to develop a way to decide which subset of these flood roads we're going to upgrade upfront ahead of time through investments in order to minimize this number of infeasible trips based on the rest of the roads that are still not upgraded. Right? So we want to design this sub-network such that the impacts that remain are as minimum as possible. And so before I tell you a little bit of more details on the algorithmic part about how we do this, I just want to emphasize the benefit of having these algorithms that allow us to find optimum or near optimum solutions in a data-driven way that we can actually evaluate under different budget constraints and resolve for multiple cost settings. So here you can see that without on the very left, without any fortification, the map is colored by how many of the trips, the outgoing trips in each census tract would actually be infeasible, will not be able to be taken under this flood scenario. And so some areas are very dark red, meaning they're highly impacted. Now, under our optimization mitigation framework, we can, with a budget of 500 meters of upgrades, we can strategically fortify only a small subset of the roads at risk and actually recover 82% of the infeasible trips. If we continue optimizing and we really insist on trying to fix almost all of the infeasible trips and essentially guarantee full mobility, to reach 99.6% of full recovery, meaning everybody can get wherever they need to, we will need about 10,000 meters. So you can see that there is a huge difference between 500 meters for 82% to 10,000 meters for 99%. So this is the kind of cost-benefit analysis that our algorithms provide, where we can see the dramatic improvements by targeted mitigation investments with a small budget, and then with increasing budgets, decreasing cost-benefit margin, which can basically guide makers how much and where to invest. Okay, so how do we go about solving this very large-scale network design problem? I mean, you see that the roads networks are quite large. So we're given this road network, which is annotated with the flood exposure and mitigation cost and our pairwise mobility needs between different locations on the map. And we want to find our flooded roads that we will mitigate, fortify, in order to maximize how many trips can be completed under the flood exposure. So the first thing that we do is we abstract this problem to a network design problem, to a graph optimization problem. And to do so, we actually first do a network contraction step, where every connected component of roads that have no risk exposure, meaning they're not at risk, gets identified and gets replaced by one single vertex because they're already connected to each other. And then the different connected components are then connected by edges, which are the flood-exposed roads that we need to choose whether to fortify or not. So if I were to fortify the road that connects the green to the purple component, then those two, now all the trips between them will be feasible. So here now we have a graph which has these vertices which are connected on flooded components, edges that are road segments, flooded road segments that we might want to upgrade. We have our edge costs, we have our budget, and we have our profit function, which is the aggregated travel demand between these unflooded components. So we sum up sub-demands that they represent. So with this abstraction in hand, we are able to identify that this problem is in fact an instance of the budget price collecting Steiner forest problem. So in operations research in AI, this is a very well-studied problem that arises actually in a lot of network design problem, and it's a very difficult problem to solve. And why is it a forest problem? Is because if we're trying to minimize our cost, we would never choose a set of roads that forms a cycle. We would always have no cycles in our solution because we can easily remove one. If there was a cycle, we would easily remove one edge and still have a connected network. Okay. So this problem is, as I said, very computationally hard, is NP hard. And it's been shown that there's no really polytime approximation algorithms for it as well. So in the past, this problem has been solved in small scales using mixed integer linear models, but they do not scale to the kind of networks that we want to do on an urban road network scale, and also greedy heuristics, which are arbitrarily bad in terms of solution quality and actually are pretty slow as well. So our approach was to basically identify a particular problem structure called restricted supermodularity that applies to our problem, and based on it develop novel scalable algorithms. So what is, just on an intuitive level, what is this restricted supermodularity? It just says that the marginal benefit of adding one more edge to our mitigation plan to a superset of edges is larger than adding it to a subset of edges. So there's compounding effects. Like the bigger the mitigation investment, the more adding one more might benefit because might connect even bigger components than before. And this obviously has to hold under our particular constraints, which are we have a budget constraint and we want our solution to have no cycles. So with this novel function characterization, we built on some algorithms that exist for this family of problems called semi-gradient ascent. So these are iterative algorithms which start with an initial solution, then simplify the solution by computing what's called a modular lower bounds for our benefits of each edge, and then in a second step uses these modular lower bounds to quickly find an improvement to the current solution and then iterate over that step. And so to use this framework, we need to obviously specialize it to our problem. So we show how to do this modular lower bounds for our problem, and we show how to compute the second step for our problem as well. So based on that, we have three new proposed algorithms called semi-grad greedy, semi-grad knapsack repair. And so we're going to compare these three new algorithms to the greedy baseline, which basically just adds one edge, one road segment at a time, the one that results in the best mobility gain given our partial solution. And what we discover here in the top, you're going to see the comparison of our three algorithms, blue, yellow, and red, to the greedy algorithm, the improvement in solution quality over greedy. And in the top plot, you will see the runtime comparison of the greedy algorithm in black to our algorithms. So the red and yellow, which are our two semi-gradient iterative algorithms, we can see that they provide great improvements in terms of solution quality. In fact, for medium budgets on the x-axis, you can see that they can provide up to 1,000 improvement in solution quality. And when you look at the runtimes, they're always below the black bar, so they're faster, moderately faster. So we have one set of algorithms that provides much better quality for slightly faster runtime. And then the blue algorithm, which is the knapsack repair, you can see that in the runtime, it doesn't even show up at the bottom. It's because it's so fast that it doesn't even show up on the scale. It's 1,000 times faster than the greedy algorithm. And from the top plot, we can see that the blue algorithm provides almost the same quality of solutions as greedy. So if you want speed, you can get almost the same quality solutions, but 1,000 times faster. If you want quality, you can use our semi-grad algorithm to get much better solution for about the same time or slightly faster. So we have improved on both metrics, solution quality and runtime. And this work was presented, published in the conference, International Conference on Tools with Artificial Intelligence in 2019. So that's great. We have now a way to do mitigation planning for road network infrastructure. But the critical component of that framework was knowing the mobility needs, the number of daily trips that we'll need from one census tract to another. And what we quickly discovered as we were trying to expand our use case study to more places is that there's very limited publicly available data on mobility, and even non-publicly available for each city. It will depend how much their Department of Transportation is tracking those things and estimating these origin destination matrices. So in most cases, to facilitate and remove that dependence, what we would want is we want a way to actually predict these mobility needs. So we are in a common real-world workflow where not all the data needed for planning and optimization is available. First, we need to predict some components, and then based on those predictions, optimize. In our case, we'll need to predict the mobility, the daily travel flows between pairs of census tracts. So the first question we ask is, can we build such predictive models that are based on a rich data set, such as geographic characteristics, census, and job data? And can we build such mobility models that actually generalize to new cities? So most of the mobility prediction work that has been previously done is within a city, right? So they have some data within one city, they divide it into some subset for training, and then predict for the rest of the city. This is not our setting. We want to be able to go to a city that might not have mobility travel data, and we want to be able to predict it. So it's a quite a big ask from the machine learning model to be able to generalize to a new, completely new location. And the second important question that we need to ask is, well, okay, even if we can predict relatively accurate based on accuracy metrics, what does that mean for the optimization? How would errors in the predictions influence our mitigation planning that is based on those predictions, right? So that's a very important question, because in a sense, at the end of the day, what we care about is what is the decision quality that we achieve with our overall process. So let's first look at the first task. Can we create a machine learning model for mobility flows that generalize to new cities? To evaluate this, we collect data from 3 big urban areas, Washington, D.C., Seattle, and Chicago, and have mobility data between every pair of census tracts within them. So that means that we have a data set for training and testing our predictive model that are on the order of 2 million pairs of census tracts and their corresponding mobilities for Washington, 500,000 for Seattle, and almost 6 million pairs in Chicago. So what we're going to do here is we're going to do what's called threefold cross-validation in machine learning, meaning we're going to train using data from 2 cities and apply our model on the 3rd city where the data has not been seen by the machine learning model, and do that 3 times for each of the city being the test city, and then estimate our accuracy of model performance based on that. So we set up a comparison with traditional mobility flow models, such as the gravity model here on the left and the intervening opportunity model in the middle, which are, very well established ways of modeling mobility. However, they take very little data into account. They're based on analytical formulas that mostly depend on either the distance between 2 locations or the number or the population of each location. So the gravity model is just looking at essentially the characteristics of the origin and destination. The intervening opportunity models is also looking at the nearby alternatives of where people might decide to go. But both of them are relatively simple. Instead, in our models, based on machine learning, we basically use similar structure, but we characterize the origin and the destination by many more features. We look at population density, land use, number of jobs, urban cover, etc., and similarly for the intervening opportunities between them. So these are highly parameterized models, but all of these features can be computed based on publicly available data such as census, USGS, etc. And so here in the table below, what you can see is that the learning-based model at the bottom, based on random forest and extended gravity, are beating all of the traditional models on all four metrics that we have, on R-square, root mean square error, as well as mobility-specific metrics called CPC. So we are performing much better at achieving these generalization tasks to new locations. In particular, some of the features that our models are looking at, extracted from the American Community Service Census and USGS, are things like population density, area, low, medium, and high intensity development areas, forest, employed population, unemployed population, jobs, per capita income, etc., as well as intervening opportunities such as the number of people living between the origin and destination, how many jobs there are between the origin and destination, etc. So this framework provides for a much more, again, as I said, general and parameterized framework, and can in fact lead to some further insight in generally in terms of understanding mobility needs. So now we have our prediction models, and obviously this data is noisy, and these models are not perfect. We saw that the R-square was about 0.6. So they make mistakes. They overestimate and underestimate the mobility needs for different locations. So here comes our second critical problem. How do these prediction errors of over and underestimation affect our downstream mitigation planning? So what we discover is that although there is such over and underestimation that is spatially heterogeneous across the areas, when we compare the planning done using the ground truth, the real mobility flows, versus the planning done with the predictions from the random forest in red and the other ML model, gravity exponential, in blue, the actual mitigation plans and their benefit evaluated with the actual mobility flow, the ground truth mobility flow, is about the same. So these predictive models are making slight errors in terms of the precise number of trips they're predicting, but they're actually guiding the mitigation planning prioritization in the right direction that is congruent with what we have done if we had all the data available. So that is very, very promising result that basically enables and builds confidence in being able to propose these mitigation plans even when mobility data is not readily available, but has to be estimated from socioeconomic factors. So I want to just briefly mention that actually the work in my group on mobility and flood risk resilience started before the CIRI grant in 2017, where we entered the United Nations Challenge on data for climate action, where they basically called on different teams across the world to propose computation and data-driven approaches to inform sustainable development goals. And we basically worked on this infrastructure planning for mobility during floods in a simplified setting, but applied it to data that the UN challenge provided on Senegal in terms of mobility from their cell phone provider, flood risks, and roads. And in fact, my team with my 2 PhD students here in the picture won the area in terms of climate adaptation. So I have shown you our progress on doing the network design mitigation planning for flood risk exposure of road infrastructure. Now let me move to the water resilience part, where we, again, are aiming to select components of our network, particular pipes to upgrade in order to provide water connectivity to critical customers and coverage for all households within 1 mile. This problem was done in close collaboration with local stakeholders here in Los Angeles. In fact, the specific formulation in terms of what the critical customers are and, for example, the coverage by 1 mile comes directly from the resilience plan of Los Angeles, which is a very comprehensive document But one of the main actions within it are to advance seismic safety, prioritize most vulnerable buildings, infrastructure, and systems. In particular, in that plan, Los Angeles outlines the priority of building the seismic resilient pipe network, where their goal is exactly that, to upgrade specific pipes to these higher quality pipes in order to provide connectivity to critical customers and have 1 mile coverage. So we basically connected with them, and we realized that although this is part of their resilience plan, they didn't really have the computational tools to make it happen, to decide actually what this mitigation plan looks like. And in fact, currently, most of the operations are done on case-by-case basis, right? So there's no master plan of which pipes needs to be upgraded, but when there's an opportunity to have a repair, they decide whether to use the seismic pipe or not. The problem with that is that obviously, as I have been emphasizing all along, these mitigation plans are in the context of these large networks, and each component alone, its benefit cannot be estimated in isolation of what's happening in the rest of the network. So we need to have this global view. We need to have a plan that takes into account how the different components play with each other in order to maximize the benefit of our mitigation investment. And so that's exactly what we are trying to provide for them. And so there's these two complex constraints. We need to provide connectivity to the critical customers, and we need to make sure that all the households or all the parcels are within 1 mile of this network of pipes that's either upgraded or not exposed to earthquake hazard. So the data that we're going to use for these studies, we're going to obviously have our infrastructure data, which is the actual water pipe network with pipes and joints, and the water sources, which are pumps, trunk lines that have already been fortified, etc. The location of all the critical customers on this road network, and the hazard data. So we have the earthquake scenarios in terms of, they were provided to us in terms of fault zones and liquefaction zones. So anything within a half mile from a fault is basically part of the earthquake scenario, and all liquefaction areas are also part of the earthquake scenario. And just to give you a sense, even planning for a 4x4 mile area already involves more than 3,000 pipes and more than 2,000 pipe junctions nodes. So this planning problem very quickly explodes in complexity. So similarly to the previous problem, what we'll do is we'll abstract this specific civil engineering planning problem into a graph optimization problem. So we have a set of pipes, which are the edges in our graph. We're going to have the intersection of pipes as our vertices, including things like pump stations and valves. And so all of these form an undirected graph that represents the water network. And every edge in this graph will have associated costs in terms of upgrading it, fortifying it as part of our mitigation plan to the seismic resilient pipe. In addition to this data, we're also given a subset of the nodes that represent the water sources, right? So where we can we have guaranteed water flowing during the earthquake scenario, and the subset of nodes that represent the critical customers. Where are those evacuation centers, fire departments, etc., on the road network? And finally, we have a set of residential areas, which are basically defined by a subset of the pipes that are within 1 mile of each desired location that needs to be covered. So obviously we have many of those red blobs, one for each household or each parcel, that basically identifies all the nearby pipes that are within 1 mile that can provide coverage for it. And so with this in hand, we want to select a subset of these edges or pipes to minimize the cost such that we meet our two constraints. Every critical customer is connected to a water source, and every residential area has at least one edge, one pipe selected for to be part of the resilient network. So we have these node constraints and coverage constraints. So similar to the previous problem, this is an instance of the Steinert network problem, but with different kind of structure because it has these coverage constraints that are actually something that has not been commonly considered in the network design literature. Again, the problem is NP-hard and doesn't really have a good approximation guarantees. So for this problem, we're actually able to identify a mathematical formulation based on flows that can encode the problem as a mixed integer linear program. The nice part about this is that it means that we can tap into existing commercial strength solvers for mixed integer linear programs that can guarantee finding optimum solution to this problem. So we're able to distill down the problem to a set of linear constraints, a linear objective, and a mixture of discrete and continuous variables. So the key part here in terms of modeling is to identify the fact that we can take for each water source, inject what we call flow into it, which is going to basically represent the connectivity, and make each customer and each selected edge sync 1 unit of flow, and then provide the flow conservation constraints. That guarantees that anything that we select, any edge that you select for upgrade has to be connected to the water source, so it's not just dangling around, like not actually serving any kind of connectivity needs. And every critical customer here in yellow star is also connected to the water source. And finally, we have at the end here constraint number 7, which guarantees the coverage constraints. The nice part about this is that this formulation is linear in the size of the number of pipes and the number of nodes in the graph. And before even we apply this formulation, we are actually able to use the same graph contraction technique based on connected components that I explained to you earlier in the context of road fortification. So let's see what happens when we use this optimization framework for our earthquake resilience problem. We apply this to 3 locations on the map of Los Angeles, and we expand the area that we plan from 2 by 2 mile to 4 by 4 miles, 6 by 6, 8 by 8, in order to evaluate the scalability of our problem. And so here you can see on the right the plot in terms of runtime, and see that even though the size of the problem is growing very quickly as we increase the footprint that we are trying to optimize, the time is increasing only linearly. Although generally these problems are NP-hard, and we could have expected a much worse scalability in terms of number of pipes. The other important thing to note is that our optimum approach generates solutions that are between 6 to 23% better quality than the ones obtained by the simple iterative algorithm that basically decides one pipe at a time, adding the one that provides the best marginal benefit to the solution, which is kind of the straightforward heuristic that is used in practice when the engineers, the planners are just deciding piecemeal by piecemeal which pipe to upgrade. So when we apply our model to an entire service zone, which actually is the planning unit that a Department of Water and Power, such as the LADWP, would use, that has around more than 34,000 pipes and 300 critical customers. So under our earthquake hazard, we discovered that more than 8,000 of those pipes are actually at hazard risk, and 93 customers would not be connected to water if mitigation planning is not taken. So our approach is actually able to find an optimum solution for the mitigation plan for this entire service zone in only 18 minutes, and is able to propose a set of pipes that span only about less than 34 miles that will guarantee that all of these 93 critical customers are now connected with resilient pipes to the water supply. We are currently working closely with the Los Angeles Department of Water and Power, and have applied this model to multiple zones, and in fact are providing this methodology as a tool, as a package that they'll be able to use in-house to do their mitigation planning as things change on the ground and replan for themselves. And we're hoping that in the future we are able to expand this from the specific collaboration with LADWP to other locations across the U.S. and really make this into a strong tool that can be used by any jurisdiction that has a similar problem. So in conclusion, I guess my experience with doing that and what I want to promote is that data and AI algorithms jointly can really help inform critical infrastructure planning. It can help us identify which are the components that are most at risk. We can identify who is affected and how much, how are these risks and disruptions distributed across space and populations. And based on that information, using AI algorithms such as the one that I presented today, we can plan near optimally upgrades to maximize resilience. So use the limited resources that government and local agencies have to the best effect possible and provide a methodology and tools that, again, help them study systematically the trade-offs between optimizing different metrics, and provide in-depth cost-benefit analysis that can dramatically improve the effectiveness on the ground of these efforts. So with that, I just want to point out to the references where this work has been published, if you're interested, and just want to thank CIRI again for funding this work and supporting these efforts. And I'm open to answer any questions that you may have.
Hi, I have a question. Can you hear me?
Yeah.
Okay. I have a question about the first part of the presentation with, sorry about that, with the transportation and flood mitigation. When you do the prediction across the 3 cities, I'm wondering how that prediction generalizes to other cities that are maybe mid-size or smaller size or have various characteristics, and if that affects the optimization for the mitigation.
That's a very good question. In fact, most likely there is a difference in terms of the driving factors of mobility in large urban areas, like the 3 ones that we considered, versus like mid-size or even more rural ones. And so what I would suggest for this framework to work, we would need to identify kind of a distribution of the type of cities that we feel the mobility is more or less driven by the same factors, and create models for those, and specialized models for others. So there could be a mobility model for large urban areas, mid-sized urban areas, and small urban areas, as opposed to trying to get a single model that would work across everything, right? And so overall, so far, what I have seen is that people have shown just that it works within one city to predict mobility in one area from data from another area from the same city. We have shown that we can do it from city to city in the context of 3 cities that are kind of similar to each other. And I think it will be great to be able to show it for a bigger distribution of cities. So one challenge that we faced was exactly the motivation for our work is that we couldn't get access to, the mobility matrices for many cities, where so that we could apply our model more broadly. And so I will be very interested in connecting with anybody who might have such data and would like to work with us on doing a larger scale study on these mobility prediction models.
Hello. I was wondering if any of this work has made it into specifically the FEMA-approved hazard mitigation plans for the city of Los Angeles or the Washington, D.C., for example?
No, it has not. But you're asking about the road infrastructure, right? So I have been in close contact with some FEMA representatives from Region 9, which is my region. And there's a lot of interest in doing that, in understanding more how this can be useful. In fact, I recently presented at a FEMA workshop on data inventories for resilience planning. And during that workshop where I presented some of this work, I got interest from several kind of city managers. Like one was from one group from Honolulu that wanted to use this for their mitigation planning that they were just starting, and another one from the Bay Area. So I think definitely there's interest. I would like to see this propagate into actual policy, and I'm hoping that that will happen. I generally will need more work, more support to do that. So one thing that I think is very important, and something that CIRI has helped with, is connecting me as a computer scientist, right, an algorithmic data person, to the right stakeholders that will help me, that have already helped me, first of all, identify the right problems to work on that are relevant to what their needs are. But then now at this phase, that after we've developed the technology, of how to go the extra mile of actually putting it into the hands of those that might actually take it into the last mile of using it. So I'm, again, very open to any suggestions or connections that you can provide.
We have a question in the chat. Can you run simulations for drinking water quality in pipes? Can you detect the spread of containment in a system in close to real time?
Not in my work. So I know that there are people working on this kind of simulator models. We are working more on the mitigation planning, which is this analysis ahead of time of what components of the infrastructure should be upgraded now, such that when the disaster strikes, the overall functioning of the system is better. So to some extent, we're not addressing the disaster response part of this. Did that answer your question, Roy?
Yes, you did. I was thinking just more of terrorist use of the water pipe system and some kind of modeling of could you help identify what the spread of a contaminant might be, maybe even prior to release, just looking at vulnerable pipe entries.
Right. So that in fact, there was some a couple of years back, this big data challenge, the Battle of the Water Networks, I believe it was called, that was run by EPA, that tried to basically engage computer scientists to think about algorithmic solutions to a problem similar to what you're mentioning, in terms of thinking about possible contamination scenarios and planning ahead of time, for example, where sensors should be placed in order to maximize the speed to detecting such things. So I think similarly to that, maybe from a fortification point of view, one could think about ways of maybe making parts of the infrastructure, let's say of the water infrastructure, more resilient in terms of not being accessible for contamination, in order to similarly kind of minimize the possible ways that one can attack it. So that's not a problem I have worked on, but it's actually very related and could definitely benefit from some of the algorithmic ideas that I presented today. So I would definitely think a little bit more about how to formalize this and see how to leverage the same algorithmic advancements in that context.
Thank you.
Somebody asks in the network, in the chat, about where did I get the data from. So as I said, from the get-go, this was a very close collaboration with the LA Department of Water and Power and LA City as a whole. So when the project started, we actually obtained a non-disclosure agreement. So they've actually shared with us all of the LA water infrastructure, and we are working again with them to to apply the model to that and provide back to them the results, as well as the tool and training to use it in-house. So all of this is based on the water distribution network for Los Angeles City. And so obviously some of the plots that I showed and the results in the paper were based on not the real data, because we are not allowed to actually show pictures of the real data, and they're based on basically using a road network as a surrogate for water pipes, just for the publication purposes. But for our work, we are actually working with the real data with LADWP. How did you go about selecting drivers predictors for the mobility prediction model? Very good question, and I think there's a lot that can be added to that. We basically reviewed the literature, some of the transportation literature on mobility, and looked at what other studies have identified in different contexts as possible drivers, and intersected that with what we can actually assess from publicly available data sources like the American Community Survey and USGS. And that's what we used. We tried to be as comprehensive as possible, but I'm sure that there's many more things that we can put in there. One thing, again, to keep in mind with machine learning is that one worry is that if you put too many predictors and not actually using domain expertise to filter the ones that are actually supposed to be relevant, you might kind of overfit to these too many predictors and not have good generalization performance. So I think moving forward, two things. One is having more cities, right? So that it's not only this threefold comparison. And second, working more closely with transportation experts to identify what additional driving factors we are missing that they know from their domain expertise that should be there. In fact, already like just presenting these results to some experts in mobility, the first question that they ask and that we're hoping to follow up on is, okay, well, so this machine learning model already has way more predictors than the gravity model and previously used things that just look at population. So which of those, let's say 20 features, 30 features that we have were actually the ones that the model used the most, that are the most important? And we are trying to follow up and basically introspect the machine learning models in terms of this feature importance that will then can provide kind of hypothesis for the transportation folks in terms of what are some factors that they might not have thought about or that should be further investigated from a domain point of view. Where did you find the available mobility data? Good question. This was actually through a collaborator at Georgia Tech who works in urban planning, who had basically had worked with these municipalities and had permission to use their data and to share it with us. So it was, again, not necessarily publicly available data on a website where you can readily download it. We had to use contacts to get to it. So that again emphasizes the fact that obviously mitigation planning departments within local agencies should be able to talk directly to their DOTs, but often those those requests are hard to make. And so I feel that having, or they just might not be available. So having tools to actually get these estimates easily from publicly available data is very empowering.
We have about 2 minutes here. If there's any more questions, please keep them coming.
Yeah,
really great questions today.
Yeah, for the lively discussion, I really appreciate that engagement.
Well, if there's no more questions, we did record this series, as we do all of them, and it will be posted to the CIRI website. If there's a question that you didn't get to ask, please feel free to shoot us an email. And join us on April 29th, where Dr. Iris Tien will be talking about her project characterizing end-to-end risk of the telecommunications supply chain. Thank you all again for joining. Bistra, thank you very much for the great work that you continue to do, and we look forward to following you and see where we can go with this thing. So,
thank you for having me, and thank you everybody for listening.